Depression of freezing point. It is also a colligative property. First, what is freezing point? The temperature at which liquid converted to solid. The temperature is known as freezing point. For example, water freezing point is 0 degree centigrade. At 0 degree centigrade, water converted to ice, liquid converted to solid. Now, what is the depression of freezing point? Suppose this one is solvent. Its freezing point is TB naught, TF naught. To this we add small amount of solute. Solute is added. Then it gives rise to solution. Then it converted to solution. Suppose TF is freezing point of the solution. The difference in freezing point of solution and solvent is known as depression in freezing point. We can write relation delta TF, that is equal to TF naught minus TF. The difference in freezing point of solvent and solution is known as depression in freezing point. When we add non-volatile solute to the solvent converted to solution, at the same time freezing point of the solution decreases. Suppose this one is water. Water is solvent here. Its freezing point 0 degrees centigrade. When we add glucose or starch or urea to the water, then it converted to its solution. Its freezing point is less than 0 degree centigrade. That means minus 0.1 degree centigrade or minus 0.2 degree centigrade. Difference between these two freezing points is known as depression in freezing point. In case of boiling point, from solvent to solution, boiling point increases. That is known as elevation of boiling point. In case of freezing point decreases. Because it is known as depression. Depression of freezing point. Both depression of freezing point and elevation of boiling point, both are colligative properties. That means properties which are depend on the number of solute particles. We can draw a graph for the depression in freezing point. This one is vapor pressure column, temperature column. We know that vapor pressure of solvent, that is always higher. Solvent. Suppose we add non-volatile solute to the solvent, its vapor pressure decreases, this one. And as temperature decreases, vapor pressure of both solvent and solution decreases. Solvent and solution decreases. At certain temperature, like this temperature, at certain temperature, this liquid solvent, it is converted to solid state. It solidifies. When it converted to solid, its vapor pressure steeply decreases, maximum decreases, because vapor pressure of solids always very less compared to the liquids. In case of solution, it also converted to solid, but it requires some more cooling. Suppose solvent solidify at this temperature, its solution solidify at this temperature. This one is TF naught and this one is TF. Why? In case of solvent, only one type of molecules are present, but in case of solution, two type of molecules are present, solvent molecules and solute molecules. Because it is heterogeneous, it contains two different molecules. Heterogeneous medium, it has more energy. Heterogeneous always more energy than homogeneous medium. It contains more energy, so it requires more cooling to convert into solid. This difference, freezing point difference of solvent and solution, this one is denoted by delta TF. It is nothing but depression in freezing point. This difference is nothing but delta P. That is lowering in vapor pressure or vapor pressure difference between solvent and solution. As this gap increases, here also increases. This difference is also increases. So we can relate delta P is directly proportional to delta P proportional to or delta TF, it is proportional to delta P. Let this one is equation 1. And we know that delta P, difference in vapor pressure of solvent and solution, that is directly proportional to number of solute particles, nothing but mole fraction of solute. Equation 2. From 1 and 2 we can write delta TF is proportional to mole fraction of the solute. Depression in freezing point is directly proportional to mole fraction of the solute. Delta TF, that is equal to some constant K into mole fraction of solute, means number of moles of solute by total moles, N1 plus N2. When compared with solvent moles, solute moles can be neglected. So delta TF, that is equal to K into N2 by N1, because N1 plus N2 almost equal to N1. Delta TF, that is equal to K into N2 means number of moles of solute, we can write weight of solute by molecular weight of solute, into N1 means weight of solvent by molecular weight of solvent. So it converted to M1 by W1. Delta TF, that is equal to K is proportionality constant and M1 is molecular weight of the solvent. Both are constants. So you can write new constant Kf into here weight of solute by molecular weight of solute into 1 by weight of solvent in kilograms. If we take in kilograms, then this one is equal to molality. Suppose here weight of solvent in grams, then we can write into by 1000 here, M by 1000. Okay. This new constant Kf is known as cryoscopic constant. Kf, it is known as cryoscopic constant. Suppose molarity value is equal to 1, then Kf is equal to delta Tf. That means for 1 molar solution, not molar, molal. 1 molar solution, molar means molarity 1. For 1 molar solution, the depression in freezing point of solution is called cryoscopic constant. Its units Kf, that is equal to delta Tf by M. That means units are Kelvin, kg, mole inverse. These are the units of the cryoscopic constant. We can write some more relations. Kf, that is equal to RT naught square by 1000 into IF. Here IF is the latent heat of fusion of 1 gram of solvent. IF, that is equal to delta HF by M1. Here delta HF is the latent heat of fusion of the 1 mole of solvent. It can substitute in this one. It can be substituted in this one. We get another relation. Here R is the gas constant and T naught is the freezing point of the solvent. Okay, these are the relations for the cryoscopic constant Kf.